Welcome to the Cosmic Pie Podcast, episode 28, season number 4. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
We are broadcasting live from the campus of the University of North Dakota. Robert, we also have a chat feature, and if anyone has any comments or questions they'd like to send in while we do this podcast, of course, we encourage everybody to use that.
Yeah. I'll ignore you either way. No, not really.
Robert, want to start with
Yes.
the disclaimer, old buddy?
Okay, time for the disclaimer. That being, the opinions expressed in this show are those of myself and Wayne. They are not to reflect the opinions or policies of the University of North Dakota, the College of Arts and Sciences, the Department of Physics and Astrophysics. Just us, folks. You got to come for us.
Just us. And if, by the way, if you do like this podcast, remember to give us a thumbs up. Subscribe if you haven't subscribed. And the other thing is, for those of you who like to see us on a different media platform like Spotify, I do upload the very next day. So if you check us out, you could watch us now and then watch us again. And again. And again.
And again. Yeah. Watch as many times as you want to. Yeah.
And you always pick up new things anyways, like anything else that you watch over and over, right?
That's it. And we've already got a comment complimenting the hats. So, yeah, Wayne and I both are wearing hats.
Actually, and mine has a nice C on it. You know what that stands for?
No, I don't.
That stands for CHART, Completely Hackable Amateur Radio Telescope.
Oh, okay.
And it's the merch I got last summer when I was in Winona State University to attend a workshop, how to construct their radio telescope for detection of hydrogen gas in the Milky Way, the 21 centimeter wavelength.
Yeah, we ought to include a segment on that in our show. Building your own radioscope.
Yeah, and actually, as you know, Robert, and most people don't, of course, I'm in the process of constructing 8 of these.
Mm-hmm.
So we have 8 of these aluminum horn antennas already built, and now what I'm doing is building a wooden sort of cradle so that I can rotate the antennas at different angles with respect to the ground to make different observations. And yeah, we could show people that. And the beauty about using them is you have to just go out when the Milky Way is kind of in the right location above your horizon. You don't have to wait necessarily at night.
Right.
So in fact, during the podcast, later on in the fall, the Milky Way is like in a real good position. So maybe we can do a remote, Robert. You can be at the controls and I'll be outside or something with my phone and showing everybody, in real time, the detection of hydrogen gas in the arms of the Milky Way. So that'd be kind of cool. We should do that.
And it's like I used to tell students all the time, astronomy is something you do in the cold and the dark. Unless you're a radio astronomer, and you do that anytime.
Yeah. Or you're detecting neutrinos.
There you go, yeah.
Or you're a solar astronomer, and we'll say a little bit about the sun later on today in this podcast. Of course,
excellent.
You're not going to go out at night, right, to watch the suns.
I don't know. It might be a little cooler.
Well, that's the joke about going to the sun, right? It's too hot. How do you get close to the sun to take measurement? You go at night.
Yep.
Anyways.
That's it.
Let's start off with our very first news item. So we're going to have several sort of these update type of things that I wanted to discuss today. The first one is related to SpaceX's launch of Starship Flight 13 back on July 24th. The amazing thing about this, if you watched it or heard about it afterwards, is that when the top of the stack, so the very top of the rocket, the so-called ship as they call it, the part that ultimately will go into orbit, if I'm not mistaken, I think SpaceX, Elon Musk, has mentioned on social media that Starship 14 launch, which hopefully will be later on this month, chances are that the top part is going to go into orbit for the first time. And so it's going to be a little different than what he's done previously, which is these suborbital flights that test the heat shield and other things. But the interesting thing about this is that it landed in the water on a soft touchdown using its rockets. And it was so soft, the touchdown, that it didn't break apart when it smacked into the Indian Ocean. And so this thing is airtight. Obviously it's designed to go into space, ultimately carry people. And it floated. So there's enough buoyancy there that it could float. And it floated day after day. And now it's a navigation hazard, right?
Right.
So You got to worry about that. You don't want to leave that floating around in the ocean on its own, going to random locations. And so after several days, I think SpaceX realized, well, the thing's not going to sink. Maybe we should go out and recover it. And of course, you can get a lot of useful information about it, right? You can look in detail of the tiles that they have it so allow it to re-enter safely, not cause any burn through. So you can do close-up examination of the tiles to see how well they held up under normal flight conditions, and all kinds of things you could look at, I'm sure. The engineers would love to get their hands on this. So SpaceX finally made the decision to actually try to bring it back to shore, bring it back to land. So they went out there with a ship, I think it was 2 of them, and put these sort of, you could see these floating sort of structures that they made to line around it to help give it some additional buoyancy so that they could be able to tow it to shore. And they started that process of towing, and I noticed a couple of days ago Elon Musk had a statement, and I haven't seen an update on this recently, that they encountered a lot of bad weather, so high seas, rough seas, and that the chances of ship making it to shore was pretty small, pretty remote. So they're thinking that it's probably going to go under because of the stormy weather. Now, I didn't hear anything more about that, so I don't know what the status is of this vehicle right now, if it made it through that, is in calmer seas or not, to try to bring it back, but we'll see. Anyways, it's interesting nevertheless. So this is definitely an evolving type of project, and also very important. People kind of forget a lot about that stuff, but it's important. It's important from the fact that this is one of only 2 ways of landing on the moon for humans in the Artemis project.
So, yeah, then this one in Blue Origin, right?
Yeah, exactly. And just an update on Blue Origin. So remember, Robert, they were trying to launch a rocket, and on a test on the launch pad down at the Kennedy Space Center, the whole thing blew up. You remember that?
I do remember that.
And what's your favorite saying when something it doesn't blow up? What does it do?
It does not blow up. It is a rapid, unscheduled disassembly, RUD.
For us common folks, it's explosion.
Right. No, RUD.
Yeah. And so their rocket, their New Glenn rocket, which is what they're using to carry up heavy payload into orbit, then was kind of on a pause right now as they figure out exactly what happened. And then a few days ago, Blue Origin actually announced what happened, so they know what the cause of the explosion was. They've taken steps to mitigate that explosion possibility going forward in the future. So they're hoping, I think, to start launching probably near the end of the year. They have to fix up the launch pad. It took a lot of damage. Like, you're talking months of reconstruction here.
Yeah.
So it's not an overnight thing, right? So, and that rocket was fully fueled, ready to go on the test. Yeah. So it was like a huge bomb going off.
Yeah.
So you can imagine how much damage was actually done, even though it was all concrete and metal around there still. Right, there's a lot of stuff that needs to be repaired.
Probably required a complete refit of all the metal, because the concrete's going to say, huh, something happened?
Yeah. So Starship needs to work, right? We need this thing to get into space and to prove itself so that we can employ it through the Artemis, and Artemis 4, I guess, would be the landing one. And Artemis 3, they want to use them, either this one or the one from Blue Origin or both, to sort of testing rendezvous with the craft. And then Artemis 4 would be the landing of humans on. And when you think about that, that's such an aggressive sort of jump, right? Going from rendezvousing with these spacecraft in Earth orbit, and they're not even outfitted probably to contain an environment for humans, and then using it to actually land on the moon on the next flight and then returning, like lifting off from the moon. I can bet there would be somebody would say maybe we should have one more test before Artemis 4, where humans actually can go inside of this vehicle and make sure everything's working properly and stuff, right? You don't want to be on Artemis 4. That's what I'm saying. That's what I guess I'm saying.
Except, there's decision paralysis. You can, I need one more pass, one more test, all day long and twice on Sunday, and you're putting off the inevitable. Sooner or later, somebody's got to take the leap. Somebody's got to say, this is it.
Well, just don't be Boeing,
Oh, no.
because Boeing, I
Boing,
think,
boing, boing.
they jumped too
Yeah.
fast on it. They should have had a
Yeah.
unhuman test in addition
Well,
to what they had done before to make sure all the thrusters were going to work properly instead of putting people
right.
on there.
This gets into people complain and get upset a few years back when NASA had a rocket that blew up on the launch pad or just after launch. And see, they can't do anything. You know, these test launches are when you want things to blow up. You know, let's find the problems now when it doesn't really matter so that when it matters, of course it goes smoothly, you know?
Yeah, exactly. Well, speaking about things that are happening tonight and tomorrow night, that's the thing, the Perseid Meteor shower. So these are one of these events, Robert, I look forward to. Like, I don't want to date myself, but I've been watching these for decades.
Yep.
In particular, I always remember the one back in the mid-1990s where the comet that's responsible for the material, the dust particles, if you like, that enters the Earth's atmosphere as we see as these shooting stars for the Perseid meteor shower, Swift-Tuttle. That comet went by the inner part of the solar system and kind of repopulated the orbit with a fresh supply of material. And in that year, I'm trying to think of the exact, I think it was 94, but don't hold me to that. It's around that time that we had a fantastic shower. And I remember watching it. There was like literally fireballs, as we say, coming in, from the shower itself, all coming from the same point, radiant as we call it. It's near the constellation Perseid, which is the name of the meteor shower itself. But that was one of the best Perseid meteor shower displays I've ever seen in my life.
Yeah.
And
this is one of the big ones, if I remember. It's one that can get up to 100 or so meteors per hour, if I remember.
It can. I mean, there are other ones that are larger, but they, at least for us here in North America where we're living, those usually occur in colder times, like in like in November or even in January. There's, different things like that. But there's several throughout the years, not just the one. This is going to be the most popular, most well-known. And, of course, it's smack in the middle of summer, if you like, at the time when people can be out at campgrounds, right? Yeah. You're sleeping in a tent and your head's poking out the end of the tent in your sleeping bag all curled up with your mosquito repellent on, with your jug of hot chocolate beside you, looking up at the stars at night. I mean, how good can you get compared to that?
Right, because I know I'm not going out and standing outside for an hour or two in January, February here.
No.
That's just not going to happen.
Yeah, you'd have to be dressed up pretty warm and battery-powered everything, different heat sources. Yeah. Right? Anyways, so this is a good one to watch. So why I say 11th and 12th is because the peak is somewhere in between the two. It's like in the daytime early on the 12th. So that makes the tonight, Tuesday night, and Wednesday night kind of prime opportunity. And the best time to observe, people always ask this, is after midnight. And that's because the point of the sky where these shooting stars seem to originate from rises high in the sky. It's not below or on the horizon, and that allows you to see more of the shooting stars. But if you can't do that, like you have to work, get up early in the morning, just go out as soon as it gets dark and look up. You never know what you're going to see, right? Don't wait till midnight if it's too late, but still enjoy the shower.
Yeah.
And
you won't get clean though, so don't think you're going to be able to skip.
You just took that away. I was going to say, and this is the only shower, or one of the only showers where you don't have to bring an umbrella.
Sorry, I beat you to the punch.
You did. You got me. And just to kind of illustrate, where do these showers come from? Like I said, there's more than one shower. There's like a dozen or so. I can't remember the actual number. And some of these showers actually fade out over time, so people don't even notice that they're there anymore, and the new ones can appear. And that's because of that debris that's left over from comets in their orbits. So in this slide, you can see the orbit of Comet Swift-Tuttle and all that sort of debris that follows the orbit as the comet moves through. All these particles separate from the body of the comet, but they're still moving. They're still maintaining roughly the same orbit that the comet is on. And sometimes that orbit, then, even though the comet's not there, intercepts the location of the Earth, and you get a lot of this debris entering our atmosphere, and we see it as these shooting stars. So, and there are several of these because there are more than one comet, of course. There are many, many comets have come and gone. And so you can have many different showers. So, but this is always, just from nostalgia, then I find the Perseid Meteor shower like the best of all of them from that point of view. Now, speaking about things going on, of course, tomorrow, and depends where you live for this one, we have a total solar eclipse of the sun happening on August the 12th, on Wednesday. Now, if you're lucky enough to either be in Greenland, and this would have to be on the east side of Greenland, or you could be in Iceland in the right spot there on the western end, or if you happen to find yourself in the tip of Portugal or in Spain, you're going to see potentially the total eclipse of the sun itself. So you have to be in that, if you like, that path of totality, as we call it. So on the map that you see here, that red band, then if you're inside that red band, you're going to see the sun completely blocked by the moon itself. And that's where you can see the corona. And if any of you have seen the solar eclipse a couple of years ago, back in April of 24, or was the other one before that, August of 17, I remember, 2017?
17, I believe, yeah.
Yeah. You have to be in that path of totality if you want to see the dramatic effect of the corona. If you're in a location nearby where even if 99% of the sun is covered by the moon, it's still not good enough. You've got to go to the spot where it's 100% covered. And that'll allow you to see the faint corona that otherwise would be invisible to your eyes. Now, of course, from Grand Forks, where we're located, if we were going to see this eclipse, Robert, we'd be doing this podcast from somewhere in Europe probably, because we'd already be there ready to see the eclipse. But because we are broadcasting live from Grand Forks, that means we are not going to be able to see the total eclipse. What we can see from here, though, unfortunately, is only a very, very small fraction of the sun will be covered by the moon. And at its peak, it's about a little over 2% of the sun will be covered. Yeah. And this will occur locally for us then at 12:03 p.m. Central Daylight Time. And I do have my solar eclipse glasses. So even if the weather cooperates, I will go outside just before that time and look at the coverage of the sun. But it's not going to be a big thing, big spectacular type thing. Only a small little sliver of the sun will be missing for a period of time. Yep. But if
now,
yeah,
go ahead. I was just going to put out something there because there's a lot of confusion about total solar eclipses. It is safe to look at the sun during totality. When the sun is completely covered, you do not need special glasses or filters. The problem is if you look before that, or you're still looking as the sun emerges from behind the moon, now you're in trouble. So the way I did it at the last solar eclipse when I was in Ohio, I set a timer for about a minute before the totality was going to end. So I watched and enjoyed it. And when that timer went off, I looked anywhere but that direction. So despite what you hear, there is no harm in looking at a total solar eclipse. It is not more dangerous or anything like that unless you linger in your watching until it ends, at which point the sun comes back out, your eyes are dilated, and yes, then it's more dangerous.
Yeah, that's a good point. In fact, the last eclipse I looked at, so I saw the one in August of 2017. Actually traveled down to Nebraska to get into Path of Totality. And then I went to New Brunswick on the east coast of Canada for the one in April in 2024. And by that time, there was actually an app that I purchased. It was very low cost that I had on my phone running. And it actually, based on your GPS coordinates, it would tell you and give you a countdown, so an audio countdown so you could hear it. You didn't have to look at anything. It would tell you how many seconds there were to go before the eclipse began, the total eclipse, telling you when it was safe so you could remove your eclipse glasses, and then it would give you a warning, a countdown of when it got to the end of the eclipse. So you had time to either look away or put your eclipse glasses back on. And I found that was extremely handy. So there will be other eclipses coming up. There's one again next summer, And I think you have to be in Egypt, like in Luxor, Egypt, and so on. The path of totality goes through there. The one I'm planning to go to, if it all works out okay, is the one on July 22nd in 2028, and that's in Sydney, Australia. So
I hope you get there.
That's going to pass right over the city itself, and of course interior to Australia first. And that's going to be, what a way to go to Australia. You go, if you've never been there before, you get to check out the country and then enjoy hopefully clear weather for the solar eclipse. So that'll be nice.
Yep.
So we have to we'll see how that plays out. But very cool. If you've never seen a solar eclipse before, a total solar eclipse, not a partial, a total. And if you ever get the chance, please do it. Go see it. You will not be disappointed. I guarantee it.
There you go.
Now, speaking about our sun, I noticed on the news a few days ago, they released the highest resolution view ever of the sun's surface. And this is actually done by a relatively new telescope that's run by the National Science Foundation. At least they paid for it. And it's located in the great state of Hawaii. And it's named after a senator of Hawaii, Inouye, Daniel Inouye. And so the telescope itself is about 4 meters in diameter. And Robert, when you think of that right away, it's like, wait a minute. When I take my amateur telescope and I want to look at the sun, there's a couple of different ways I can do that. But one of the ways is I actually make it smaller by putting a block in front of the opening of the telescope and just have a much narrow opening. And so you reduce the amount of heat that's going against the optics and to potentially warp it and cause damage to the telescope. But this telescope was 4 meters, but of course it is specially designed to observe the sun. It's a solar telescope, not one to look at stars and galaxies and that sort of stuff in the night sky. And with the large aperture, the large size of the mirror, that provides you a much higher resolution than if you compared it to, let's say, an amateur telescope with like 2-inch aperture sort of opening to the telescope itself. So you're getting the very high resolution, and the images that you're seeing on the right side of the slide gives you some idea of very, very high resolution that you can get. In fact, it is so high resolution that you can actually see the Kelvin-Helmholtz instabilities in the interfaces of the different gases traveling at different velocities due to difference in temperature, the temperature gradient across the area of the sun where you see these sun complexes, the sunspot complexes occurring. It's amazing the amount of detail that you can see.
Yeah.
So
now, I'm again going to say something that's trying to put things in perspective. The average insolation, the amount of energy from the sun hitting the Earth at the surface, averages out to about 1,000 watts per square meter. So this telescope is on the order of, let's see, that area would be what, 16 times 3, 48 square meters? So that's 48,000 watts. It takes 300 watts to run a dryer through a cycle. So just normally, every square meter of ground can power 3 dryers. And this is 48,000 times that.
yeah, and you could do that rough calculation. So it's circular mirror, so pi r squared.
Right.
So the radius is 2 meters, so 2 squared is 4. So 4 times pi is 3, right? So that's 12, roughly 12 square meters would be the size.
So what I was getting at is this thing is absorbing a lot of energy. I would love to see the structures they use to dissipate that safely so that it doesn't melt the mirror itself.
All I know is I haven't looked at it in detail, but it's a very detailed type of instrument and a lot of money, as you can imagine, to construct it. And it took a while, right? If I remember right? It's not something you build in 1 month. So, but the amount of payback you're getting now is incredible. You know what would be better than this?
What's that?
Having that same telescope in space.
Oh, yeah.
Because you get much sharper view, of course, above the disturbing effect of Earth's atmosphere.
Yeah, because that's one of the problems, too, is you're looking at the sun, so you're looking directly into the heat energy that is disturbing the atmosphere and making things, quote-unquote, twinkle. So the effect on the sun is when you're looking at the sun is even worse than looking at a star at night. So this is a phenomenal instrument.
For sure.
All the way around.
Yeah, exactly. And speaking about something that's bright, well, not as bright as our sun, of course, is we have another comet to talk about. This is Comet McNaught. Now, this comet was extremely faint, and it didn't really, come to the foreground in terms of people talking about it because it was so faint. In fact, at one time, it was like 17th magnitude. So it's like, you need a pretty large, even amateur telescope to see that, right? You're in a good view would be a professional-sized telescope at that point. But what happened was, and so this comet, just to kind of pick up the story in the right spot here, is it actually passed the closest point to the sun in its orbit, is perihelion, way back on June the 14th. And around that time, shortly thereafter, it actually increased dramatically in brightness, like thousands of times increase in brightness. And what happened, it appears, is that it broke apart a bit. And some of the pieces, if you like, probably came off. And of course, you get fresh, gases that are exposed to the ultraviolet light from the sun, and you energize that fresh gas. And of course, it releases a tremendous amount of light in the process. So it increased in brightness dramatically. And in fact, this happened again recently. It actually, in total, it went up to about 10,000 increase in brightness. So it went from about 17th magnitude, apparent magnitude, to 7, which is
That's almost naked eye.
Yeah, it's also almost naked eye visibility in a dark location. So I checked last night to see what it was at, and a lot of people were reporting it down around 7th magnitude. But the idea, they're keeping an eye on this. And by the way, if you want to see the comet itself, if you have like a small telescope or large binoculars, you should be able to pick it up. And it's in the eastern sky, like a lot of these are when you're just passing by the sun, in the eastern sky just before sunrise. So it's in the constellation Cetus. So that's between Taurus and Pisces, and sort of in this perspective, south of Aries. So, and there you can see it's not too far away from the constellation Orion, so maybe you can recognize that rising early in the morning. And get out there and have a look. If you have a nice clear view towards the east, this is a perfect opportunity to see it. The interesting thing about this comet is we just don't quite know what's going to happen. So people speculate if we get a large sort of disruption or break apart of the comet, a large piece come off, it could increase dramatically in brightness, and you could easily see it with the unaided eye. Wouldn't that be something?
That would be nice.
So
Southern Hemisphere seems to get all the nice comets.
Well, you know what they say about comets in terms of predictability, right?
They're not.
They're not. And so there's a lot of red-faced astronomers that have come and gone because of trying to predict what's going to happen to a specific comet.
Yep.
Even Comet Halley back in 1986 was one of those, and there have been many other examples, way before my time of this sort of stuff happening. So you just never know with comets. But the only one thing I always look for, as long as it doesn't hit us, I don't care what really happens to the comet, right?
Right.
Just don't make it across our orbit at the same time we're there.
Just keep on trucking.
Take a look, but keep going.
Yeah.
Now, speaking about the constellation Orion, our favorite star in that constellation is... Robert, what's our favorite star?
Betelgeuse.
To what?
Betelgeuse. Because you can't say the other version of its name 3 times.
Yes, just don't say it 3 times, right? So Betelgeuse, right? And Betelgeuse was in the news, especially way back in the late 2019 going into 2020. Maybe, Robert, you want to say why it was in the news? And
because it dimmed dramatically. It went from, it was still one of the brightest stars in the Northern Hemisphere sky, but people were stepping outside at night and with no training, no unaided eye, no telescope, no binoculars, noticed how dim it got. And we didn't know why. Speculation went wild that it was about to go supernova because it is due any astronomically speaking day now to do just that. It is clearly going through the final stretch of its lifetime. So people started making all kinds of guesses as to what was going on. And then we made it turns out that, it's ejected gas and dust that it burped out, if you will, and blocked its light for a little while. But then people started asking the question, why did that happen? And this slide is about the answer.
Well, it's interesting. At that time, back in 2019, when Betelgeuse underwent this great dimming event, as we call it, it's normally the brightest star in the constellation Orion. And I distinctly remember going outside at night here in Grand Forks, looking up at the constellation, and easily telling it was no longer the brightest star.
It wasn't even the second brightest star there for a bit.
It really dramatically got faint, really noticeable to the eye. And then if you step outside, let's say tomorrow morning, early before sunrise, when it's still a little dark, and look at Orion, because you'll be able to see it in the east, and you look at Betelgeuse, you can tell it's the brightest star in the constellation. So clearly the brightness has changed in real time. It's not one of these, a lot of times, in astronomy, you got to wait for 10,000 years for something to change. You always hear about, I got to wait, this is not going to happen until 2048, and I don't know if I'll be around then. Always hear this kind of stuff. But these are changes that happen over literally days and weeks.
Yep.
And that doesn't happen a lot.
It doesn't. And, there are a few objects I can think of where various observations have shown they change rapidly on a human time scale. But most of those are not microscopic. Everybody can see them like this.
Yeah, that's the thing. You don't need a telescope. You didn't need binoculars. As long as your eyesight was reasonable or correctable with glasses, you could see the change in brightness.
Mm-hmm.
Now, that caught a lot of people's attention, obviously. And because of that, there was a lot of detailed study of Betelgeuse. What is its nature? Robert, we don't even really have a nice, precise distance measurement to Betelgeuse.
Right. It's because it's so bright. We can't take short enough exposures. Well, you need longer exposures to get the resolution that you need, but it's so bright that it saturates pixels at those exposure lengths, and you can't get a measure of its brightness and size.
So a lot of the distant measurements of nearby stars, relatively speaking, is done now with the Gaia spacecraft, which no longer is working, but they're still analyzing the data from it. And Gaia made measurements of over 1 billion stars. And we used the parallax technique. Now, Rob, would you like to maybe explain that a little bit to people who are unfamiliar with it?
So parallax is a known property of geometry, and it's basically that, you can experience it yourself. If you hold your thumb out in front of your eyes and you blink one eye, close one eye, and then you close the other, you'll notice your thumb shift from one side to the other. And there's an own geometric relationship between how much of a shift there is, how distant your two observation point, your two eyes, are, and you can get the distance to the object. Pure geometry. And Gaia is a spacecraft that allowed us to measure the very tiny movements of stars because they're just that far away.
And the thing is, Gaia was in space. That is, it's not a telescope observing from the Earth. And once again, you don't have to look through that blurring effect of our atmosphere. So that made these type of really, really tiny angles be able to be perceived for a large number of stars at various distances. And the thing
I think it even got some that were in Andromeda.
Yeah, some nearby galaxies definitely in the local group were actually observed too. And one of the things that it couldn't do was to give a really precise measurement of the distance to Betelgeuse, because as you mentioned already, the detector that you're using on board that spacecraft, the light coming from Betelgeuse is so strong, relatively speaking, that it will saturate the detector. And so you don't get the precise measurement that you need. It actually forces you to look at dimmer stars, not necessarily ones further away, just dimmer. So it's the brightness that really matters here, not the distance.
Yeah.
And so there's still a very large, relatively speaking, uncertainty on the distance to Betelgeuse. Some numbers people have tossed around because it's important when you're trying to do modeling, which was done extensively after the Great Dimming event. some of the numbers tossed around are in the order of like 500 light years away or so.
Right.
So it's on that order. But anyways.
It's somewhere in that range, but yeah.
Yeah, I'm sure that we'll be able to put up some kind of nano satellite in the future that would have a small enough detector that's not too sensitive, that's designed to measure, the astrometry, the
position,
the position change, the parallax measurement of some of these really bright stars, so we can really nail down the uncertainty to their measurements of their distances.
Right.
That's something that seems like it'll be doable at some point. But
at some point.
Yeah, but what came out of all that new attention, if you like, on Betelgeuse was the discovery of a star that's actually orbiting Betelgeuse itself, Betelgeuse proper. So we give a name Betelgeuse B, where the main star is the one that we knew about all along since antiquity, Betelgeuse A. Now, the thing is, Betelgeuse is not constant in brightness, and I don't mean just the great dimming event that happened. Betelgeuse regularly changes in brightness. And some of it is its brightness changes that you can't really notice with the eye, so you need to track accurately the brightness with a telescope, and you can watch it change with time. You make what we call a light curve. And when you make light curves, that's just the change in brightness with literally time, you can look at that curve and actually can see if there's more than one change going on. So, for example, Betelgeuse may change in brightness over a period of 100 days. So it takes 100 days to go from maximum brightness down to minimum brightness back up to maximum again. But superimpose on that period maybe another period, maybe, 10 years or something, a subtle change. So it's more of a complex situation where you have all these periodicities, as we call them, all intertwined with different physical processes that are occurring within the star itself. And one of the ones that bothered people, in the sense that it was very mysterious, is the one that's associated with the orbiting of a companion star. So one of the periods is due to the fact that Betelgeuse A is not all alone. There's actually a companion star. In fact, the companion star, and this image that you see here taken with the very large telescope down in Chile, it's geared up the instrument in such a way that it subtracts the light, or at least as best it can, from the bright red giant that is Betelgeuse proper, Betelgeuse A as we're calling it now. You subtract that from the image. And what you see left over then is this companion star, a clear image of it, Betelgeuse B. And over time, you can actually see Betelgeuse B change in position as the two objects are orbiting around their center of mass.
And the big point is it's changing its position and doing so in a way consistent with Kepler's laws.
And with that period change that was observed, or at least one of the periods. The other interesting fact about this, so if you wait long enough, you'll see the positions change. But the other really interesting thing is this star is so close to Betelgeuse A, it's orbiting inside of its atmosphere. Get that one.
Yep.
So,
and
wow.
This is the lifespan difference and everything of these high mass stars, because Betelgeuse is about ready to go supernova. Okay, its companion Betelgeuse B is an A-type star, so it's a massive star itself with a very short lifespan, and it's not close to going supernova. But Betelgeuse over there is, because it's that much more massive. So when you get up to these O, B, and A stars, holy cow!
Well, Betelgeuse B. Now, like I said, there's an uncertainty in the distance, which propagates to uncertainty in the mass. So the estimated mass is between 2 and 3 solar masses for Betelgeuse B.
Oh,
so it will
they've cut it down then.
Yeah, so from this study anyways, it will not go supernova. It's less than 8 times the mass of the sun when it's a main sequence star.
Okay.
But here's the thing to consider, and there's a big but here. Is this star is orbiting inside of the atmosphere of Betelgeuse A. What was its mass before it did so? That is, for Betelgeuse A, when it was not as extensive, not as large, because that's a natural thing that happens late in its life when it blows up as a red giant or an asymptotic giant branch star, even a red supergiant star, which Betelgeuse A is. this Betelgeuse B would have been outside of the atmosphere. And how quickly does Betelgeuse A expand outward so that Betelgeuse B is now inside of its atmosphere and maybe being torn apart, if you get my drift there. So we're not seeing the initial conditions necessarily, the exact initial conditions. We're seeing obviously what it looks like today, and modifications have happened to Betelgeuse B. It's got to be losing some of its mass, some of its atmosphere as it continues to orbit inside of Betelgeuse A. In fact, I wouldn't object to the idea that it's slowly spiraling inwards.
Right. It would almost have to be. There would be just an incredible level of drag.
Yeah, so that's the dynamical friction, as we call it in physics. The
but we do have a question.
Term. Yep.
Will Betelgeuse B be destroyed when Betelgeuse A goes supernova?
Chances are yes.
Chances are yes.
And if not, it's going to be dramatically different. I could see a lot more of its outer atmosphere being completely torn apart, leaving it with a little core nugget left over somehow. That would be the only thing that would potentially survive. In fact, this is not well studied, to be honest. Right? Because
it doesn't happen.
Well, it happens, but I mean, how many of these star systems do we have where we see the object before it goes supernova and we see a stellar companion orbiting around it, around the center of mass? We don't really see that too often. And then for it to go supernova in our lifetimes and then see what's left over, that's what you really want. Right? How do you know what happened to it? Wait till it explodes and then look to see if it's still there. That's how you know. And that's incredibly difficult, right, to do that. It'd be so rare of an event to be able to do those type of observations.
To me, it's just yet another reason to be going, come on, blow up already.
Well, the way our luck is, Robert, it'll blow like the day after we die or something,
Right. Don't get me started. You're dead on with that one.
But it's very interesting, nevertheless. Now, think about something that's interesting and something that I partaked into, because I got caught up in the hype with it all, was the impact, and we mentioned this on our last podcast, right? The impact of the upper stage of the Falcon 9 rocket from SpaceX on the moon. So this was back on August the 5th. So this would have been last Wednesday. And I was out there, so it was due to happen at 1:35 a.m. was the estimated time for us. So yes, it was clear that night. And I think correct me if I'm wrong, Robert, you were out to the observatory, so it was clear. You were doing
I was out at the observatory, running it for a grad student. Yep.
And you didn't look at the moon because why?
Because I was more interested in where the telescope was pointed and what it was looking at.
And didn't you forget about it too or something?
And then I forgot it completely about it.
That's what I was looking for. It happens.
Otherwise, I'd have probably had the other telescope pointed at it. So
taking a peek. So anyways, I had my telescope out, and of course, no pun intended, I was focused on the right side of the moon, where the impact was supposed to occur. And the hope was that it would create a large enough disturbance that we'd see the plume of material as it rose to the upper part of the, away from the surface of the moon with the sun reflecting off of it. That was sort of the idea. It was right on the edge of the moon anyway, so it would have been a hard observation to make. I didn't see anything in my telescope, and just to let people know, my telescope is a Dobsonian, a 12-inch Dobsonian, so it's not like a little tiny telescope. So if there was something dramatic, I should have saw it. I didn't see it. And at the same time, there was multitude of people broadcasting live on YouTube with much larger telescopes, robotic telescopes, and they were all saying the same thing, that the time came and went and nobody saw anything. And the idea was, maybe nothing happened. And then it was just like the day later, then the word started coming out that, yeah, indeed, some people did see it. In fact, what you see here is an image taken of the moon from a spacecraft that I forgot all about, that it's in orbit around the moon for several years now. It was put up there by South Korea. So they have a lunar orbiter that's, in orbit obviously around the moon itself, and it was taking images of the area where they thought that the impact should occur, and lo and behold, it captured the sign of an impact. And you can see that even in the unzoomed image, the one with the nice smaller square, and at the very center of that you can see sort of dark soil. And if you looked at the zoom version on the right with the dotted circles surrounding it, you can clearly see a darkened area, and that's the site of freshly exposed regolith that you can see then compared to the surrounding areas. That's the impact of the upper stage of the Falcon 9. So it did hit. I mean, we have clear evidence of that. And lots of reports were coming in. Others had seen it. Larger telescopes down in Chile had reported seeing it. And this was, again, the very large telescope, the VLT down in Chile, which is about, I think it's like 8.2 meters in diameter. So it's a big telescope. It's not a small telescope. They actually caught spectra. So they were set up to observe spectra of the debris. And when they looked at the debris, they saw signatures of both sodium and lithium in the debris cloud in the plume that rose above the edge of the moon itself. So I thought that was quite interesting, Robert, to see that. And you can see the spectrum here labeled.
Well, and because sodium and lithium are both fairly rare elements. So when you see a plume of containing a reasonably high concentration of both, in the spectrum, it's probably artificial. And so it was a rocket body at the moon.
Yeah, and it's interesting because the sodium lines and stuff are such that you can see it, in the right range of wavelengths, right? If it's a signature that's way off in the infrared, if you don't have an infrared detector with the spectrograph, I mean, you can't see it, obviously, right?
Right.
So it's a play off between what detector you have at your disposal in terms of wavelength coverage and what type of spectra you can predict that would be, created during the impact. So it's a combination of the two things.
Yep.
And of course, a lot of luck.
And a lot of luck. Yeah.
Anyways, so yeah, it was interesting. So that was actually observed, and you get some interesting science out of that. It's like, it's not just a novelty, just something happened. Oh, that's cool. Move on. There's some interesting thing. Yourself, one of the primary labs that a person could do in introductory astronomy class is dropping objects of different masses onto a surface like, powder or something to get an idea of what is the impact crater that gets left behind.
Right.
And so there's a lot of science related to the geology, the structure of the soil, a regolith in this case, that you can get given the energy of the collision and so on.
Yeah, I think that would be a neat little test bed study, whatever you want to call it, is to put in front of intro students, is to not just vary the height, but vary the structure, maybe a layer of sand and a layer of clay, and go down to rock and see how a layered structure changes the crater shape and diameter and size. I'll have to think on that.
Well, what I'd love to happen is land a robotic rover, right near the impact site and have it be able to the ability to crawl down into the crater and sample that freshly exposed soil.
Oh yeah. Oh,
because you're digging down how long? 100 feet at least down in, right? If not more. And that's a soil that's been unexposed to sunlight.
Right.
And so you never know.
Our solar wind, all that stuff.
Yeah, so you never know what you'd see, right? It's sort of primordial in that sense, right? So
I will not disagree. Hey, let's do it.
Yeah. Now, one of the things, of course, when you're talking about different discoveries like on the moon or elsewhere, of course, is we put up space-based telescopes. So this is kind of the primary thing I wanted to talk about today, even though the podcast is almost over because there's a lot of news items. But some people, someone come to you and say, the James Webb Space Telescope, that was launched Christmas Day back in 2021. So it's been up there for a while, right? Nearly 5 years. In fact, the nominal lifetime before launch was 5 years.
Right.
And it just so happened that they were able to put the telescope on station where it's ready to make observations and use a lot less fuel than what they had thought. So it gave it sort of double the lifetime. So expected in total it would last at least 10 years. And that's a great thing because it costs billions of dollars. You want the thing to last as long as possible. So you could ask, that we're almost halfway through the mission, let's say, what is one of the most important or interesting or unplanned serendipity, if you like, discoveries that the James Webb Space Telescope has made? And I think at the very top of your list would be the discovery of these things, known as little red dots. Now, the terminology doesn't really justify the significance of these things. But what happened is that people, years before the telescope is put in space, scientists get together and they propose different ideas. Well, when the telescope was finally launched, I wanted to do to observe A, B, C, and D. And then other scientists have their own wish lists also. And so people get together, form collaborations, and eventually there are panels of astronomers that determined who should get major time on the telescope, at least for the first large surveys that are to be carried out. And remember, when you put a telescope like this in space, number one, you're not going to get to it to fix anything that goes wrong. And the other thing is you don't know how long it's going to last.
Mm-hmm.
So you want to be able to try to squeeze as much good science out of this instrument as early as possible, just in case some mechanical issue crops up and the thing only lasted 2 years. And you're like, why did you waste your time looking at sort of hum-hole things when we could use the Hubble for that or some other ground-based telescope? Why didn't you go after the really interesting things? So that's the decision-making process that is undertaken before the telescope even gets to the rocket stage of it. So one of the early surveys that was done was to look out as deep as possible. And when I mean deep, I mean distance-wise. And not only that, I also mean time-wise. To look out at the universe that's so far away, you are looking back literally 12 billion plus years into the past to try to survey as much as you can to understand what the universe was like shortly after the Big Bang.
Because that has a bearing on all of the cosmology, galaxy formation, all of this. It gets down to our core understanding of the universe itself.
It's the evolution of the universe as we know it. It's an extremely important topic. So in one of these early surveys that was done, and this is the image you see here in front of you with a sort of an insert with a zoomed in region, one of the things that was discovered were there are these little tiny red spots. At first, you think, oh, there's something wrong with the image processing. What are they? Now, it turns out that these objects are real. They are there. They're not an artifact of the image. They're not a detector flaws or something like that. And immediately what you would think then is, well, how come the Hubble Space Telescope didn't find these things? And so you take an image of an area of the sky, which was also taken by Hubble. Of course, the James Webb is more sensitive to longer wavelengths to the infrared than the Hubble. And it has a much larger mirror, so we can see fainter things, has a larger light gathering ability. And when you actually look in the same region as the Hubble, those objects were in the Hubble images, but their signal to noise was low enough it didn't stand out as being something weird or different than the surrounding objects. It was only by looking at longer wavelengths and with the larger mirror that you could notice that there was something unusual here. And so since that time, and that's just shortly after the Hubble was making its observation, since that time, people have wondered then, what are these little red dots? Okay, what are these objects? And are they unique? So here in this slide, this is a zoomed in view. This was a study that was published back in 2024 of one of these red dots. Now, there was a lot of speculation, but of course you can speculate all you want, but at some point you need to sit down and think, what are the observations? What are the measurements I need to make in order to see if the ideal I have is consistent with the data? And a lot of the speculation surrounded on black holes, that these could be the center regions of some compact galaxies. And you see the tremendous amount of light coming off of them because of the interaction of material outside of the event horizon of these potentially newly formed black holes. Now, some of these objects, of course, are what you really want to do is not just take an image like you see here. What you really want to do is be able to take spectra of these objects. And this is where the interesting thing happened. for the brighter ones that we're able to get a good measurement of the spectra of these objects, they're all high redshift, Robert.
Yeah.
Some of these are being viewed literally 600 million years after the Big Bang. 600 million years. And if these turn out to be massive black holes, you're now constraining time. You have 600 million years to form these suckers. That's all the time you have. That's the maximum amount. You don't have billions of years to form these supermassive black holes. You're down to just hundreds of millions. So, the constraint on your models is getting very tight. Now, you might wonder, how many of these things have we seen? Well, we've detected over 300 of these. This is like 300, almost 350 of them to date. And I'm sure there's more and more out there as well. As more observations come in different areas, we'll see more of these things.
Yeah.
But the
And we do.
Go ahead.
We do have a question, but I'm going to speak on an analogy first. When we started seeing protoplanetary disks around stars after we discovered our first exoplanets, the same type of shift in thinking happened. When I was a kid in high school and middle school, planet formation took billions of years. Okay. And all of a sudden they started aging these stars and the ones that had debris disks. And we had to change that thinking because the stars had blown away their gas and dust, the disks around them that planets could form in and from within 100 million years. And so this is a similar situation. We know the universe's age. It's pretty tightly constrained. And so these things being that close to the beginning puts some pretty tight constraints on galaxy formation and everything. But the question is, theoretically speaking, what if you had a mirror, say, the size of Texas, how far it could be perceived? So I'll let you lead into that one.
Well, you'd have to do the area of Texas. You'd have and there's a direct relationship between the area of the light gathering ability and how faint you can see. I don't know, and I can't do that calculation in my head.
Right.
But clearly, it's just a ratio of the area of the mirror. For example, with the James Webb Space Telescope, it's about 6.5 meters in diameter. So you can calculate, if you assume it's a perfect circle, you can do pi r squared and figure out the collecting area. And then it's just the ratio of the area to Texas to the area of the mirror. But the thing about it is that our universe is finite in size. Why? Because, maybe, I should put a caveat there. It's finite in time.
Right.
And if the universe is 13.8 billion years old, so that means it's finite in size if you think about what you can observe. That's the caveat on that. For example, when the universe formed, the furthest light could have traveled since the formation of our universe is 13.8 billion light years. It could not have traveled any further than that because there hasn't been enough time to light to travel a further distance. So wherever you're located in the universe, even if it's an infinite universe, and we don't know if the universe is an infinite extent or not, it doesn't matter where you are in the universe. There's this horizon that surrounds you in all different directions. And if you had a telescope, you could only see out as far as you could go would be 13.8 billion light years. You can't see beyond that, even though there may be more universe beyond your horizon, because there hasn't been enough time to reach you from that distant universe. And as you wait, you allow more time to elapse. Then there's more time for light to travel from outside your observable universe to then go inside your observable horizon. Okay? And
I'm going to ask a question, though. Isn't that kind of countered, though, by the fact that the universe is expanding?
That's the thing. And
so there's actually a hard horizon out there somewhere where you just can't see past it.
Right. And the other thing is that you think the furthest you can see out, like say a galaxy, if one galaxy formed right at the beginning of the universe, the furthest or most distant galaxy you could see is 13.8 billion light years. But because of the expansion of the universe, that galaxy today, whose light left 13.8 billion years ago, has been en route towards you ever since. You can ask the question, where is that parent galaxy, the source of that light? Well, because of the expanding of the universe, it's over 40 billion light years away.
Right.
But that still leaves you with this observational horizon around you.
Right.
So, and the other thing you worry about is the further away objects are, the faster they're moving relative to you. So there's some point where you reach the speed of light and you can't see beyond that. And that's another type of horizon.
Right. So the bottom line, there are limits. There's things it doesn't matter how big a telescope you have. It doesn't matter how much technology you develop. The universe itself conspires against you.
Yeah, you can't see beyond a certain distance. You can certainly see fainter things if you had a larger telescope. So that would be the advantage of something in the area of Texas would be you see a lot fainter things. So what you can see in your observable universe, you'd be able to study in greater detail. Now,
there we go.
Getting back to the little red dots, right? Because, like I said, some people suggest that they are these black holes, supermassive black holes. Other people are thinking, this is what this slide illustrates, that maybe they're just supermassive stars that ultimately would collapse to form these massive black holes to begin with. So as the interplay of the material surrounding these stars, they give rise to their reddish color. So you can come up with various models, for example, to try to explain all this. The problem in all this, you can come up with 10 different models that suggest 10 different things. That's the progenitor of these little red dots. But how do you test them? And science, is you've got to come up with a way of testing. It's not just, a belief system tossing an ideal out there with no evidence, or doesn't matter what you do, you can't say if it's right or wrong. It has to be testable. That's how science progresses. And so in all these detailed models that scientists come up with, there has to be predictions. You say, if you looked here, or if you did this careful observation, you will see this if my model is true, or at least is consistent with the model. And that's the kind of things that we look for in science, including astronomy.
Indeed. It's got to be testable. You got to predict something that we can then go out and look for. So
now, one of the things, of course, to get detailed analysis, to get detailed physics of what's going on is, once again, we look at the spectrum of objects. And people have captured the spectra of these little red dots, and that's what you see in front of you here. We mentioned that already. There were redshift measurements made. So in the spectra, they do not appear to be, the typical AGN, active galactic nuclei, where you have a supermassive black hole and material that spirals around outside of the event horizon eventually crosses, but in that process, light is emitted from the vicinity of the black hole itself. They do not seem to have the same type of spectra, these little red dots. So there's something else going on. Maybe there are a special class of AGNs or active galaxies that we didn't know exist before. I mean, who knows? There's still a lot of work that needs to be done. But in my opinion, definitely the discovery of these little red dots is the most significant discovery to this point in time that's been made with the James Webb Space Telescope.
Agreed.
Now, yeah.
I mean, I'm sitting here going, I would have been shocked, but also just like, oh, heck yeah, if they'd proven to be stellar spectra, because, wow, yeah, there's your supermassive stars. Because it's stellar spectra, Yeah,
life's usually not that simple, right, Robert, as we know.
It rarely is, yeah.
Yeah, lots of stories we could tell about that, just our stuff that we do, our research.
There you go.
Yeah, but if you like to explore these type of objects, one way you can do that, of course, is go to places like the University of North Dakota, and we have lots of programs here on campus, both in humanities and in the STEM field. And one of these days, we're going to put up some nice pictures of the new STEM building that's growing in size across the street from where Robert and I are located. And you come here and take lots of classes, both on campus and also online. So you don't have to be in North Dakota if you can't make it here. Of course, you can be anywhere in the world as long as you have an internet connection. At some point, you can do the work and study from there. And so we encourage you to get involved. I mean, be a lifelong learner. The day that you die is the day that you stop learning. That's kind of what I think about.
Yep. I mean, folks, it's part of the benefits of my job here, but I'm taking classes. So you never stop. Always try to learn something. Get in there.
Now, our next podcast, of course, will be a week from today. So that's August the 18th. Boy, Robert, the summer is going fast.
Yeah. I mean, my grad students come back to campus on the 19th. So, yeah.
Things are happening, especially next week. It really gets going here on campus.
Yeah.
And the first official start of class on August the 24th after 4 p.m. The official full day of class is, of course, the next day on the 25th. And that's really where we get going. But it's, as we've said many years now, this is especially in August. This is a really exciting time to be at the University of North Dakota as it brings in a fresh supply of energy of all these new students that arrive.
It really does. It'll be hectic, but it's always fun to see too.
Yes, so. and we feed off of that energy, don't we, Robert?
We try.
When you get older, it gets a little harder, but we feed off of that energy, right? It energizes us as well as the students. So we always leave you with a quote at the end of our podcast. And I never tell Robert what it is. So if he acts surprised, it's like it's not fake, right? It's actually real. Sometimes he bursts out laughing. Sometimes he just stares at me. So today's quote is from somebody I think everybody or most people know, Arthur C. Clarke.
Clarke, yeah.
Very famous science fiction writer. In fact, his book...
He was a physicist, too.
Yeah, the book 2001: A Space Odyssey and the series that went along with that was made into a well-known movie back in the 60s, and then the follow-up 2010. Back in the 90s, I believe that one was made into a movie.
Mm-hmm.
And so the quote is from Arthur C. Clarke. So here's what he said. I don't believe in astrology. I'm a Sagittarius, and we're skeptical.
Oh, I love that one. Yep.
If you like this podcast, even if you didn't like it, please give us a thumbs up. Subscribe if you haven't subscribed, and we'll see you next time. Thank you for watching.
See you, folks.